In this lecture, we're going to basically look at the applications of Newton's laws. Okay, the first one we're going to deal with basically is friction, right? So there are essentially two kinds of friction, right? There's static friction. So surfaces not moving relative to each other. Surfaces not moving. And then there's some kinetic friction. Right? Surfaces are moving. Okay? Relative to each other, right? And so the way it works is basically always opposes motion. So for instance, if I draw a picture here, object, and I subject this object to a force, F, there will be another force of friction, which will be opposite the direction of motion, right? So basically if the velocity is this way as well, then that will oppose the motion. Now, there are other forces involved in this thing as well. So for instance, the force of gravity here gives us an object mass m, and basically the normal force here as well, right? And the force of friction, okay? So let's just write down the two possibilities for static friction. The force of friction, the maximum, is equal to mu sub s F of n. And for kinetic friction, the force of friction is equal to mu sub k F of n. Okay. Now, even though it looks like it's just a difference in the coefficient of friction, you might notice that there's a max here and no max here, right? And the reason is that this is always the value for kinetic friction, but this is the maximum value for static friction. Okay, so as an example, all right, suppose you have a really heavy car here, okay, and the brakes are locked and stuff, and you're here, and you're going to push this car, you're going to exert a force on this thing, equals 200 newtons, say, right? And the car itself basically is about 1,000 kilograms, right? So basically this is mg on it, this is Fn, right? And this car is not moving, so let's suppose the coefficient of static friction is about maybe 0.8 or something like that, right? So in this case, the normal force, because it's not falling through the road, it's just mg, okay? That's basically 1,000 kilograms times 10 meters per second squared. That is 10,000 newtons, right? So the force of friction maximum that you can get in that case is mu sub s F of n, which is 0.8 times 10,000, which is 8,000 newtons. That's the maximum force right now. If I push on the car and it is not moving with 200 newtons of force, it cannot push back with this maximum force. It actually pushes back right, with a force that exactly matches this one, right? So in this case, basically, if A equals 0, AX equals 0, that implies that the sum of the forces in the x direction equals 0, which is equal to, well, there's some F minus F of F equals 0. That's 200 newtons minus F of F. So that implies the force of friction is 200 newtons. This is the maximum. This is the actual value that has to be held to in order for the car not to move. If it pushes back with 8,000 newtons, it'll basically run you right over and crush you, right? Okay, so that's basically the key with static friction, is that like it depends, it adjusts itself such that it will prevent you from moving it, okay? Now there's a limit, right? So if you push this thing with say 9,000 newtons, that is bigger than 8,000 newtons, the maximum force they can allow, then in that case this car will start to slide. All right, so in order to basically see this in greater action, let's go basically look at some simple cases here, right? Okay, so the first thing, right, is to consider basically a plane like this, and you put a mass up here, right? And this surface here has a mu sub s, right, which is some value, but you may not know this value, right? And theta, okay? And I can adjust this thing up and down basically to see what it is, right? So the first exercise, right, is to figure out how to determine mu sub s just given this setup, okay? So we're going to determine mu sub s, right? Okay, so let's go ahead and do that. All right, so let's draw the forces in here. This is the force of gravity. This is mg. This is the normal force, Fn. You can clearly see this thing wants to slide downward, so we can immediately draw F of F in this direction. And let's give this thing a axis here. That's x and that's y. All right? Okay, so in that case, basically I know that it's not moving. A equals 0. And so that means that F net is also equal to 0. And we'll do it basically in two parts, right? We'll do the x component first, and do the y component. Actually, let's do the y component first, because that's actually a little easier. All right, so in y component, I have sum of the forces in the y direction equals 0. This is equal to Fn, that points in the positive y direction, minus, this is theta as well, mg cosine theta, right? 0, so you get this classic result for inclined plane, Fn is equal to mg cosine theta. All right, now you can check it. If you reduce theta to 0, then you know that Fn is equal to mg, and in fact cosine of 0 is 1, so in fact you get that answer back. So that checks out. All right, so now let's do the x-axis. So the x component, sum of the forces in the x direction equals 0. Well, let's see. So I have a component along this way. So that's minus mg sine of theta, and then plus f of f equals 0, right? So in that case, I get basically f of f is equal to mg sine theta, right? So basically, this is the value to exactly match the sliding force. Okay, that's great. Now let's go. Basically, we want to determine mu sub s, all right? And I can basically move this thing up and down, all right? So I can change theta, right? So you know, if I move this thing up and down, eventually it will reach a point that will just slide right down, right? So let's basically, if we determine that, let's try to figure out how we can figure out what theta is going to be. So at that point, it's going to reach a theta max. At theta max, f of f max is going to be equal to mg sine theta max. This is exactly equal to the maximum force of friction I can get, which is mu sub s f of n. Okay. What's mu sub s at? Mu sub s is something I don't know. F of n is something I do know. That's just mg cosine theta, right? So let's basically balance everything out. Mg sine theta max is equal to mu sub s mg cosine theta. The m's cancel out, the g's cancel out, right? And so what we have is that mu sub s is equal to sine theta max over cosine theta max, which is the tangent of theta max, right? So you can do this experiment, right? Take a inclined plane, increase the angle, and the angle at which this box starts sliding down is theta max. The tangent of that determines the property on the surface. Okay, so that is interesting, right? So let us think about how I want to do this here. Right. Okay, so let us now consider a slightly different system now. Okay, slightly more complicated. Well, I'll start drawing it here actually. So I'm going to draw something that looks something like this. So I'm going to draw the same inclined plane again, same theta, right? I'm going to draw my mass here, but rather than call it just m, I'll call it m1, right? If I have an m1, that means I have an m2 as well. Okay, and to link everything together, I'm going to put a pulley with a string. I'll drop the string, basically pulling that way. All right. So this is the second example. This is a plane and pulley system. All right. And suppose I'm going to give some value of mu sub s. I don't know what mu sub s. Well, I do know what mu sub s. Tell you what mu sub s is going to be, right? If I don't, I can always determine basically using this experiment here, right? Well, I'll just tell you what the value of mu sub s is. Okay. Suppose the same value as this before. We do the same experiment here. All right. So there are two masses, all right, and so there are basically two free body diagrams that can be done, right? So let's see. So we have to also say that it's not moving. So that means that A equals 0, which means that the net forces on 1 and 2 equals 0 as well. All right? Okay, so that's key. All right, so let's go draw this thing out. All right, so let's do basically the free body diagram for both of them. Okay, I want to do basically 2 first. 2 is easy, right? Okay, so this one has a force of gravity, which is m2g. It also has, let me just turn some extra light here. It also has a tension force in this direction. So that's the tension force. Okay. All right. Sum of the forces equals 0. That means the tension, we'll call this the y-axis here, right? Minus mg equals 0, and so you get tension is equal to mg, not m2g. Not terribly surprising, actually, at some level. All right. Okay, now let's look at m1. This also has some tension force. Okay. So for m1, there's a tension force going this way, tension force. There's a force of gravity going this way, m1g. There's a normal force going this way, Fn, and then there's possibly some force of friction going some direction. I don't know exactly which direction yet, quite yet. All right. Okay. So let's adopt a proper coordinate system for this. X and Y, say. All right. Okay. And let's just do each at a time. Right. So, always best to do y first. Let's do y first. This is actually pretty simple. You know what it is. There's going to be some of the forces in the y direction equals 0. That's going to be the normal force minus mg m1g cosine theta, right, equals 0. Classic result, Fn equals m1g cosine theta. Okay, that's the first thing. Now let's do the second one, right? Sum of the forces in the external equals 0. Now this is actually a bunch of forces here, right? So let's count them. I have a tension force and a force of friction and the gravitational force. So let's do, there's a tension force, right? That's the tension force. I have a component which is along the gravitational force, that's minus m1g sine theta. And I finally have a force of friction. I'm going to just use a positive sign right now, all right? Because I don't know exactly which direction it's going to be yet, all right? This is equal to 0, right? Okay. So, in that case, what we have is that we have f of f is equal to m1g sine theta minus t. I have t just from here. That's m1g sine theta minus m2g. Okay? So that's the second thing. Now, what's interesting about this is that this tension, this force of friction, can be positive or negative. Okay? If it's positive, right, it's basically in this direction, it's going to want to slide down. If it's negative, then basically what happens is that this object wants to slide up, all right? The force of friction always opposes the motion. Okay, so let's consider those two cases, right? So the first case is that we're going to want to slide up, right? F of f is negative, right? So, in order for this to slide up, basically I need f of f equal to f of f max, right? Because I want to break the force of friction here, right? So let's do that. So f of f, which is m1g sine theta minus m2g. Okay, so now, where f of f is negative, so I want this to be true. So this is going to have to be equal to a negative thing, so f of f max, which is minus mu sub s fn, which is in this case minus mu sub s m1g cosine theta, right? And I can ask the question basically, what value of m2 is needed to slide up? Okay, let's go figure that out. All right, so let's write everything out now. So m1g sine theta minus m2g is equal to minus mu sub s m1g cosine theta. Okay, that's just that equation right there. Let's take off all the g's now, all right? And now I could go ahead and solve for m2. m2 is equal to, see, bring this side, bring that side, so what we have end up getting is we have m1 sine of theta plus mu sub s cosine theta. And so given some angle and some mu sub s, I can determine basically, and m1, I can determine what m2 has to be for this object to slide up, right? And we did this experiment in class and we showed that it more or less worked. Now experiment 2, let's go sliding it down. Right. Now in this case, basically, let's suppose we want to f of f is positive, right? And we need f of f to be equal to f of f max now. All right? So let's write that entire thing down again. So it's going to be basically f of f is equal to m1g sine theta minus m2g is equal to, now this is with a positive sign, mu sub s f of n is mu sub s m1g cosine theta. Okay? Now, I'm going to do something slightly different. Okay? Well, let's just sort everything out first. And then we'll just figure this out. So what this ends up giving me, well, actually, let me tell you what. So let's suppose I want to find theta such that it slides down. Okay, so I have to find some theta for which this will work. Okay, so let's go ahead and try to figure this out. Okay, so the issue here is that you have cosine theta and sine theta on both sides. That makes it a lot more annoying. Let's write down the equation first on a clean sheet of paper, and then we'll go ahead and solve it. Okay, so see my paper here. All right, so write down the entire equation now. Again, this is m1g sine theta minus m2g is equal to mu sub s m1g cosine theta. All right, so now let's go ahead and we'll square everything first. m1g sine squared theta minus 2. Well, let's just kill off the g's first, right? We don't need the g's. Okay. Okay. Minus 2 m1 m2 sine theta plus m2 squared is equal to mu sub s squared m1 squared cosine squared theta. Okay. So we note that this thing here is just 1 minus sine squared theta mu sub s squared and 1 squared 1 minus sine squared theta. Okay, the sine squared on this side, we'll collect all the sine squares together, right? We'll move everything to the left hand side. So on this side I have basically m1 squared plus mu sub s squared m1 squared again sine squared theta minus 2 m1 m2 sine theta, and now this one is plus m2 squared minus mu sub s squared m1 squared. Entire thing equals 0. Okay, so you recognize this is a quadratic equation where ax squared plus bx plus c equals 0, where x is basically sine of theta. All right, so the solution is x is equal to minus b plus or minus square root of b squared minus 4ac over 2a. So let's go ahead and do that. So this is going to be sine of theta is equal to minus b, that's minus minus, that's 2 m1 m2 plus or minus square root of b squared is 4 m1 squared m2 squared minus 4ac, so it's 4 times something, unfortunately it has to be nasty, so m1 squared plus mu sub s squared m1 squared m2 squared minus mu sub s squared m1 squared, okay, divided by 2 times a, 2 times basically m1 squared plus mu sub s squared m1 squared again. Okay. Alrighty, so let's be exceptionally careful. All right. Yeah, this is just going to be a gnarly one. Let's just see if we can figure this out. Right, okay. So there's nothing we can really do, all right, to make it simpler. You have to be given values of M1 versus M2 and u sub s in order to solve this, right? So you can now, let's try some values here. Let's try M1 equals 2 kilograms. M2 equals 1 kilogram. Mu sub s equals, pick a value here. I would say this is 0.5, say. Okay, just make life a little simpler, right? Okay, so in that case, right, let's do sine of theta is equal to, let's see. So this is 2 times 2 times 1, that's 4, plus or minus the square root of, now this is just essentially that thing squared, so that's 16, minus, okay, so now this is a little more careful, we gotta be somewhat careful about this. Okay, this is gonna be 0.25 squared, so that's essentially, this is 2 squared is 4, plus 0.25 squared times 4 is plus 0.25 times 4, which is 1, that's basically 5. And this one is going to be 1 minus 0.25 times 4, that's basically 0. Oh, that makes life a lot easier. Divided by 2 times, well, this is just this bad boy again, that's just 5. Okay? All right. So this is basically 4 plus or minus 4 over 10. So either it's 0 or it is basically 0.8. Okay, so there are two possibilities. The first possibility is something that looks like that, right? Basically, the angle is 0, all right? And so at that moment, what happens is that it's going to want to start to slide. It just matches the force of friction in that case, right? So that's what that means, right? The second case is for this one, sine of 0.8, right? And let's just go ahead and figure what sine of 0.8 is. Well, I'm going to calculate with, oh, actually, I do have a calculator with me. Fortunately, it's not the best calculator. It's actually my phone. So let's go see if we figure this out. Calculator. Okay, so let's see. This is in degrees. All right, so let's see. Inverse sine of 0.8, 53 degrees. Right? Okay, perfect. All right. So that's two of them. Okay. All right, so now let's consider another one. Let's consider circular paths. All right, so last time when we discussed circular paths, we got defined. So you have a circle coming at this, right, with some velocity v, this object, all right, and it's basically some radial position r. Okay, the acceleration is basically pointing toward the origin of the circle, right? And the magnitude acceleration is AC. This is centripetal acceleration minus r hat. Okay, AC is equal to v squared over r is the centripetal acceleration. Okay, so we know that that has to be the centripetal acceleration in order to basically keep this object moving in a circle. All right. Okay, and so because of that, if you have to exert acceleration, there must be a force on this object. If this object has a mass, there must be some force there, right? So in fact, basically, A is equal to F net over m, right? And so this is the sum of all the forces over m has to equal to the centripetal acceleration minus AC r hat. Okay, the minus sign just makes sure that it points toward the center of the circle. All right. Okay, so let's basically do a few examples of this. Right. So the first one we have, let's suppose right, is that suppose you have just some object that's basically swinging around in some horizontal plane, right? And this object moves with some velocity here. Let's give some velocity equals 10 meters per second. Let's make this radius equal 1, all right, meter. And the mass is also equal to 1, all right? So in that case, we know that the net force, the magnitude net force, is equal to AC, which is V squared over R. Okay, sorry, MAC, MV squared over R. All right. So let's figure out what the magnitude net force is. So it's basically going to be 1 times 10 squared over 1, 100 newtons, basically. Okay, and which direction is it? It's pointing in towards the center of the circle. Right? Has to be. Okay, so that's the first one. The second example is a vertical loop. Okay, so suppose you basically throw a ball, it's spinning around in a circle, say, for instance, all right? And what happens is that basically it goes around the circle, and there are two positions it goes around to, all right? The bottom circle we'll call position 1, top circle we'll call position 2, all right? Okay, and for this purpose, we only need one axis, so I'll call this the y-axis, say, for instance. Right, and there's a string basically holding this ball, right? Okay, so basically at the end of the string, there's one tension here, another tension there, right? So let's go basically try to figure this out, right? The sum of the forces, which is F net, that's going to be equal to MAC. Okay, let's make the magnitude, just make it simpler. Okay, which is MV squared over R. All right, okay. So we consider two cases. One is at the top, and one is at the bottom. One is at the bottom, one is at the top. So let's basically consider case 1 first. All right. So in that case, let's draw a free body diagram for it. So what you have is that you have a force of gravity. So this gives this thing a mass m, a mass m. Force of gravity, basically mg, and you have the tension force T1. Okay. Now the sum of the forces, sum of the forces is going to be equal to T1 minus mg. This better be equal to mv squared over r, because that's the acceleration on the body. And so you get the first value, T1 is equal to mg plus v squared over r. Okay, that's the first thing. Okay. Now let's consider case 2, right, which is at the top. In that case, if you have the force of gravity, mg, also have the tension force, T2. Okay. The sum of the forces is equal to T2 minus plus mg. Well, actually, both are minus signs. All right, and that better be equal to basically the centripetal acceleration, which is pointing downward now, minus mv squared over r. We're going to turn everything to plus signs now, okay? And then you have basically T2 is equal to m g minus v squared over r. Sorry. T2 is equal to m v squared over r minus g, right? Okay, so when is the tension exactly 0? Okay, in that case, basically, it has to move just fast enough such that it closes the bar without basically falling downward, right? So you can basically compute what the minimum velocity is. So we can compute minimum right? So basically v min squared over r minus g equals 0. That's basically these. V min squared over r is equal to g, which is basically v min is equal to square root of r times g. Okay. Alrighty. Now, we're going to consider two more problems of uniform circular motion, right? So the first problem, then they're actually related. The first problem is a tether ball. Okay, so you've probably seen this basic around, like maybe your brothers or sister, even you play with at one point. There's a mass at the end of a rope, right? And this rope makes the angle theta relative to the horizon, right? And as a result, this ball basically swings around in some circle here, right? Now, let's go and break this down into proper components. This is the y-axis, this is the x-axis, say, all right? And because this thing's going to be moving around some circle, right, I know that, let's see, how do I want to say this? Let's say there's some length L, say, all right? Because it's moving around some circle here, right? I'm going to just figure out basically what's the relationship between the velocity of the ball moving around, so this is basically v, and the angle, right? Okay, so we're going to find relation between theta and v. Okay, we don't know it. All right, so I know that if I swing this really fast, the angle will open up. If I swing really slow, the angle will basically decrease. All right. Okay, so let's go look at. So there's two accelerations. The acceleration in the y direction. Well, this ball is not going up and down, so that's going to be 0. Okay. The acceleration in the x direction will capture a brief moment in time. This is actually going to be equal to minus AC x hat, right? So at that moment in time, it's going to be basically have a acceleration in this direction because it has to match the centripetal acceleration. Okay. So this first part means the sum of the forces in the y direction equals 0, right? And there's a few forces here. So there's some tension. So it's equal to some tension times cosine of theta, right? This is also theta as well, minus the force of gravity, mg. Okay? And so this first thing applies. The tension is equal to mg over cosine of theta. Okay? That was pretty simple. Now this second thing right here, ax, right? That's going to be equal to sum of the forces in the x direction. There's only one force actually, right? That's just this tension force. Tension times the sine of theta, and of course I have a minus sign because it's pointing in that direction. That's going to be equal to basically A minus AC. So the tension times the sine of theta is equal to AC, which is V squared over R. Now what is R? R is the radius of the circle, basically, that we care about, okay? All right, so we just got to be a little careful about that. So this radius, R, r is equal to L times the sine of theta, right? Because it's just basically this right triangle right there. All right. So let's put this all together. That's my tension. That's mg sine of theta over cosine of theta is equal to v squared divided by L sine of theta. Okay. So, well, I'll leave it as r for now, okay, and then we'll just sort out. So this is basically the tangent theta. So what this gives me is that, and this is equal to m. Don't forget the m there. Okay, m's cancel each other out, right? And so what this gives me is that v squared over r is equal to the tangent, g times the tangent of theta, which is equal to v squared is equal to rg tangent theta, okay? All right, now you just gotta be a little careful. This r is in fact something like that. So you just gotta be slightly careful about that sort of stuff. All right, so that's a tether ball, okay? Now, we can do one more example, right? Which is actually the same problem, but it's just couched a little differently. And this is a very common problem. It's called bank curve. Okay, so what you imagine is that you have some frictionless curve, right? And you have some mass which is sliding along this frictionless curve, right? And there's basically some value of basically theta such that this, and velocity such as this basically equals everything, right? So let's basically pick, this is the x direction, that's the let me think about how I want to do this. Right, y direction, okay. And this is slightly annoying. Okay, so there's going to be two directions first, right? So the first thing I want to pick, I'll call this y2, and this is y1. Right, you'll see y in a second. Right, so let's go along y1. This thing's just not moving along y1, it's basically staying on that surface. So in that case, basically, I know that the normal force is just mg cosine theta, okay? All right, you can figure it out, right? And now this normal force is going to push against this thing in the xy, actually no, so I got to be careful here, sorry. That's not quite right, okay? So, how do I want to say this? All right, so let's do it this way. So there's a normal force here. This is just y, okay? So there's a normal force which is going this direction, right? So the normal force, and then there's some gravity mg going this direction. So the normal force times, let's see, in this case, this is cosine theta, right? This angle right here. Oh, sorry. Right, this is also theta as well. The normal force times cosine theta in the y direction, right? Minus mg. This is equal to 0. All right, because this thing better not be sliding up and down. And in the x direction, the normal force times the sine of theta. That just should be equal to basically the acceleration, the centrifugal acceleration, which is m v squared over r. Okay? All right. So what we have here is that the normal force from this one is equal to mg cosine theta. All right? And we plug it into here. What we end up getting is that plug it in. This is going to be mg tangent theta is equal to m v squared over r. Okay, let's kill off the m's now, right? And you get the same relationship as we had before, right? Which is that r, the radius of the curvature of the bank, times g tangent theta is equal to v squared. Okay, so the same as before, right? Okay, so that's it for this lecture, right? And next we'll basically look at other stuff, right?